Hi everyone, this is a quick video on measurements in Sig Figs, and it's a good companion to the lab on measurements in Sig Figs. So the first thing is that in science we're always measuring things, trying to be quantitative or number based in our scientific reasoning. So what we want to do is look at two terms. They're often used together, accuracy and precision, but they're often used incorrectly or thought to be the same thing, but they're not. Accuracy is referring to how close a measure is to its accepted or true value. So often we don't know what the true value of something is unless we do many trials and we take an average, for example. Or we might define a standard. For example, a kilogram is defined as the mass that's actually a kilogram block that is in Paris, France. It is the definition of a kilogram. So it's sort of interesting what is considered the standard, but anyway, whatever that standard is, the closer you are to it, the more accurate you are. So this question demonstrates what accuracy is. If you're a technician measuring 1 gram on 4 balances, which of these measurements is closer, assuming the 1 gram is the accepted value, right? So in this case, the closest value to 1, or the most accurate value, is A. That's the closest one. So I think of this sort of like target practice. So you have a bullseye, and you're throwing darts at this, and let's say that the bullseye represents your true value, and when you throw a dart and it's close to the true value, then you would say that's accurate, or it's more accurate than if you threw a dart and you got out here. So this is less accurate because you're farther from that true value. True value. All right. Now precision doesn't have to do so much with the true value, although it's nice to have precision and accuracy. Precision is how fine your measurement can be, but it's also how reproducible it is. So for example, if I'm throwing darts and I'm throwing them all over here, then those measurements are close to each other, right? And so that means high precision. Unfortunately, it's not high accuracy though, right? So ultimately what I want is high precision and high accuracy. So for measurements to be close to each other, it's nice for them to have very fine measurements. So meaning the number of decimal places. I want to be able to have numbers that are very close to each other because they have more decimal places and more ability to be close to each other. So for example, 98.584, maybe I might have measurements that are decimals away from each other, but pretty much similar in many of these digits. So that would mean that I'm capable of higher precision. So when you're asked about precision, then it's nice to have values that take you out for their decimal places. So the most precise measurement, the most fine measurement, so smallest increments can be measured. You can see C. All right, now measure the arrow using the ruler. So here's where you need to do some estimation, okay? So if the length is something like that, oops, not quite. There we go. Okay, something like that. And I'm sorry, it's not that straight. We know for certain that we have 5 centimeters at least. Okay? But I can do better than that, right? It's definitely more than 5 centimeters. So I'm going to say it's 5 point something. Now it's not quite 6, and it's not 5.5. It's not 5.3. Maybe it could be 5.3. Maybe 5.1, 2, or 3, right? So I'll just write all of those down because some people might read this differently, and actually that's okay because there's some uncertainty about that decimal point. I don't know for sure if it's a 2 or a 3 or a 1. So what I would say is that it's 5.2-ish plus or minus 0.1. It's sort of above and below by 0.1. Now, instead of writing the plus or minus, I just know that this place here, that decimal place, comes from here. That's the uncertain value. So instead of writing this whole thing down, I'm just going to write 5.2. And I'm going to make sure I write the unit as well, because that's very important. But 5.2 centimeters tells me that this last digit is the estimated value. So let me write that down, because that is such an important thing. Estimated value. And this was, of course, 100% certain that it was at least 5, right? So that brings us to what sig figs are. Sig figs are your certain digits and one estimated value. And that estimated value is always your last significant figure. So these are significant figures. I'm going to write sig figs for short, or SF. Okay, so to determine how many digits or how many significant figures you record, you always have to look at the scale. And let's look at what we did here. One shortcut that I use to determine how many digits to use, how many decimal places can I record, is figure out what each increment is. In terms of this scale, each increment is 1 centimeter. So that means that you can read between centimeters, or you can read to the first decimal place, right? So I'm going to record or estimate to 1 decimal place past the increment. So since I'm in the ones place, I can go to the next decimal, which is the tenths place. If the increment was the tenths place, I would go out to the hundredths place. Hundredths place, I'd go out to the thousandths place. You can always go one more digit or one more magnitude, power of 10, smaller. Okay, let's try that here. What is the increment of each of these lines? So I know from 20 to 21, okay, so here's 21 and here's 20. I know that there's 10 lines, so each line means it's a tenth, because I have, if that's hard, here, this is 1 degree, and I'm dividing it into 10, so that's a tenth of a degree. All right, so each of these lines is a tenth of a degree, so my increment is 0.1 degree C, so I'm going to record to 1 more decimal place, or 0.01 degrees C. Okay, let's try it out. Zoom way in here. 20, 20.1. Oh, by the way, this would be 20.0 because 20.00, right? Because I'm actually going to record to 2 decimal places right here, 2 decimals. So 20.00, 20.01, 20.0, 20.1, 20.2, 20.3. Okay, so it's definitely 20.3. And then notice it's a little bit above 20.3. I have to figure out how much above that is it. So it's not halfway. It's a little bit less than that. So you can say 4 or 3 or something like that. Notice that's uncertain, right? So that's why you're not sure what that is, but you can put down what your best guess is. So if you split this into 10 lines, yeah, actually it's smaller. It looks smaller than that even, right? So do your best. Don't just put a 0 there because you don't know, but do, like, I think it's either 2 or 3 maybe. Okay, but what you're doing is subconsciously, or maybe you're trying to invisibly divide this into 10 lines and then try to figure out, oh, or maybe divide it in half and divide it in half again. Okay, so notice that it was easy to tell that you needed 2 decimal places because you were estimating that value. Now, if that was on the line, then you would still have to put a 0 there, but the 0 would tell you it was on the line, but it would tell you you're estimating it as the value 0. Okay, so the point is, for this scale, you need to have 2 decimal places. So that's always going to be dependent on your scale, how many tick marks you have, what your graduations look like. Always figure out what your increment and go 1 more decimal place past that. And I'll let you guys try this one. Report of measurement for the volume in this beaker. Go ahead and give it a try. So we know for certain that it's definitely above 300 but below 400. The marking shows certainty to the 300ths place, but the next digit is uncertain, so I can only estimate that one digit. So I think it's a slightly above halfway, so I'm just going to say it's 360, but you could equally say it was 370 maybe, right? So that's okay. So this is your certain digit, this is your estimated digit. And unfortunately, there's no units here. We should always write down our units, okay? So I'm just going to pretend it was milliliters. Now, if our estimated digit is in the tens place, even though we're not writing it down, what does that imply for its margin of error? We could have been at 370, right? So we're at plus or minus about 10 milliliters. The actual identity of that sometimes is not known. We're just estimating that it's probably about 10, just because of the way the markings are set up. So if it's plus or minus 10, are we going to be good at measuring volumes that are 5 milliliters? So I would say no, because our margin of error is much larger than what we want to measure here. So I would say no, due to greater uncertainty. Ugh, sorry, this is terrible. Due to greater uncertainty, 10 milliliters. Then what is to be measured. Okay, or something to that effect. Okay. All right. That brings me to a good point then. Okay, we're using significant figures here, and 360. How do I know it's not the 0 that's estimated? Just like here, remember if it was on the line, the 0 would be estimated? Well, how do I know this 0 is not estimated? So we have to develop some rules about when the 0 is estimated and when it's not estimated. Here it's not estimated, so we would just call this 2 sig figs. But in some cases, if it was estimated, we would have to make a notation somehow. And here's how we would do that. We would have 360 dot if this was estimated, or we would have 360 with an overbar. That's another way, if this was estimated. But if this was estimated, then I would have a much more precise beaker than this one. In fact, what would that beaker look like? In order for the ones place to be estimated, the tens place is where the increments are. So if I had a reading like 360 where the 0 was estimated, I would probably have to have 360, 370, 380. I need to have one more marking. And then the level of liquid is on the line. So I'm estimating that one last value to be a 0. So this is 3 sig figs, but this is only 2 sig figs. The more sig figs you have in general, the more precision you have. Some exceptions to that, but in general. Okay. So let's go through some of the rules for what zeros are significant after the decimal point. Usually the 0 is significant if it's at the end of a number. So 3.0, it's at the end of the number and after a decimal point. So this is implying plus or minus 0.1. That's our uncertain value. So this counts as 2 sig figs. Okay. 3.1, again, last estimated digit. So this is an error in the 10th place. So this is 2 sig figs. This is considered 3 sig figs, where the error estimated value is this last one. I'll just start circling them. The estimated digit is here, so this is implying a plus or minus 0.01. Okay, it's in the 100th place. So this is considered 3 sig figs. And here, I've got that one, and so all of these are sig figs, so 4 sig figs. And this is implying, so see how the precision's getting greater and greater, more and more precision, more and more decimal places here. 0.001. And always put your unit. Now we don't always have to write this margin of error. I'm just writing it to give you the interpretation of what I'm seeing as estimated. That tells me it's approximate margin of error. So here's another example. The 1 is uncertain, so when it's not 0, it's pretty clear that that number is estimated. Here, okay, again, same idea. There's my estimated 0, there's my estimated 0, there's my estimated 0. So just going through, I have 2 sig figs here because this is telling me I have plus or minus 0.01. Okay, I have 3 sig figs here. I have plus or minus 0.001 because these zeros are being recorded. That's telling me that they are being estimated or measured. Okay, and then here, this is sort of tricky because there's zeros everywhere. These zeros do count. Okay, so this one is the estimated value. And the sig figs on this are only the 3 and the 2 zeros at the end. These zeros only hold the place of this number, meaning it tells me it's in the thousandths place, but it doesn't tell me these zeros were measured values or estimated values. That has to be at the end of the number. So yeah, that part's a little confusing for people because they're thinking, oh, well, those numbers are significant, right? That they're important. Well, it's not just important. It has more meaning than just the magnitude. It's referring to the measurement, the estimation, the certainty. So one thing I could tell you is, let's say we converted this to scientific notation, 3.00 times 10 to the minus 3. See how these zeros can just disappear into this, okay? So what matters is this part right here. I can always convert this to liters or micrometers, microliters, or some other unit that will give me a different number. But it's this part that's important. This part can change, so depending on what unit I convert to. So it's actually the magnitude or place holding zeros don't count, because I could always convert this mathematically to another number. It's the measurement itself is really here, okay? So this is 3 sig figs, and the placeholder, or the margin of error, is in this last digit, right? So that's 1, 2, 3, 4, 5. Okay, so it's that's 1,000th, 10,000th, 100,000th of a milliliter. Okay, so just to practice, let's try telling ourselves how many sig figs are there in each of these measurements. Okay, so here's my answer, and I almost fooled myself here. All right, so in all of these, this is probably one that we didn't talk about yet. Just like how these zeros are placeholders, these zeros are also placeholders. So I only count the 3 because none of these other zeros are indicated to be measured or estimated in some way. So I'm going to just assume that the 3 is the estimated value, and this implied error would be in the 10,000ths place. Okay, so, all right. Same thing goes here, 310. The 0 is not indicated in any special way with a decimal point or an overbar. So this is, the 1 is the estimated digit. And so this is plus or minus 10 milliliters. though you don't have to write that part. But that's sort of the meaning that that's conveying. If the 0 was significant, I'd put a dot there, or I'd put a bar over the 0.